Okay, so I realized that when I made part 1 and part 2 of the kinetics videos that I left out a little bit. So this is going to be part 1.5. And we're going to start with a change in concentration with time. And so any graph that you ever see of a reaction, if we are graphing on the y-axis the concentration of some reactant, we'll just call it A, versus time, they're all going to have this general, at first the concentration of the reactant falls very rapidly, and then as it gets used up, it gets harder and harder and harder for the molecules of A to find each other, and so the reaction slows down until you reach this point where the concentration of our reactant kind of levels out at maybe wherever equilibrium is, or perhaps the reaction goes to completion and so there is no more A left, wherever it is that it levels out at. But regardless, the reaction does tend to slow down as it proceeds. Well, on the AP exam, they want you to be able to graphically determine if you have a first order reaction or a second order reaction. And the way that you do that is you take the data points that you use to make this graph right here. So the concentration of A versus time, or time versus the concentration of A. And you graph that in two ways. The first way is you graph the natural log of A versus time. And the second one is you graph 1 over the concentration of A versus time. And whichever of these two graphs gives you a straight line tells you what order reaction you have. So if you take these data points, exponential-ish decay, and you graph it, and you graph the natural log of A versus time, and it ends up looking like this. Well, that right there tells you that this is a first order reaction. If instead you graph it and you graph 1 over the concentration of A versus time, and you end up with something that looks like this, well, that tells you that it was second order. Ooh, my handwriting's going crazy. Sorry. Now, the slope of this line gives you even more information. If it's a first order reaction and you get a straight line with the natural log of A, then the slope of this line is going to be negative K. And the reason that we say it's negative K is because this line has a negative slope. And we want the value of K to be positive. And so we just say, okay, well then make this negative slope also negative, and a negative negative is a positive. So that gives us a positive value for K. If it's a second order reaction where 1 over the concentration of A gives you a straight line, then the slope of this line is going to give you K. And if you're going, okay, wait a minute, I forgot what K was. K is the rate constant. Just clean up my screen a little bit here. K is the rate constant where you have rate equals K times the concentration of A raised to some power, and then if you got something else in here, the concentration of B raised to some other power, whatever it might be. And so this K is what you can find from the slope of the straight lines. Kind of cool, huh? But you will only have to do that on a first or a second order reaction. And by do that, I mean determine whether it's first or second order graphically. You will encounter third, fourth order reactions, but you will only have to figure out graphically a first or a second order. So this is a nice little table that can help you figure out different things about a first or second order reaction. This is just your general rate law. The rate is equal to K, the rate constant, times the concentration of A, or the change in concentration of A over change of time. And this would be a second order reaction. Second order because the exponent here is a 2. Now, how you get from the differential rate law, the regular rate law you could call it, to the integrated rate law, I don't know. I have no idea. Somebody waves a magic calculus wand and you get from here to here. So who knows how that happens? It doesn't really matter to us. If you were taking calculus, maybe you can figure this out, but more power to you. And so this is just an equation that can help you figure out how much of a particular compound or chemical that you will have left at a certain time based on your starting amounts and whether you are first or second order, is whether it's going to be natural logs or 1 over. And in this half-life, there might be one question in the multiple choice or one question in the free response that asks you to calculate the half-life of some reaction. And the only really way to do that is just to memorize these two formulas. If you want to memorize them, great. If you don't, well, then you missed that question, and hopefully no harm, no foul. And then the straight line is what's going to give you a straight line in a graph. Well, if it's a first order, it's the natural log. If it's a second order, it's 1 over. And then the last one is how to find your slope. So if you're really after that 5 on the AP exam, memorizing this table should definitely be on your to-do list. Now, how is temperature going to affect the rate of a reaction? Well, typically, rate is going to increase with increasing temperature. And the reason for that is because a higher temperature implies that the particles that are reacting are moving faster and with more energy, which means you're going to have more collisions, and the collisions are going, more of the collisions are going to have the right amount of energy, which implies that you're going to have more reactions. Now, the interesting thing is that concentration changes, they're not going to change the value of K, but temperature will. So if you have your rate law, I'm just going to do a simple one right now. Little first order reaction here. If you have this rate law for your reaction and you change the concentration of A, the rate and the K value, they're going to stay the same. But if you change the temperature, the rate and the K value are going to change. And so in this case, well, the rate will change with changing. I'm sorry, I didn't mean to say that the rate won't change. It's just K. So if you change the concentration of A, K stays the same. If you change the temperature, K changes with temperature. So you have to figure out a completely different rate law. You would have to do a complete different set of experiments to figure out that rate law for the new K. Now, there's some vocab that you guys need to know and a couple of graphs that you need to know how to draw. And in our study guide that we use, we call it the Red Book. It's figure 14.6. But I'm just going to draw you the graphs that you need to know down here, and you should be able to draw these graphs just from scratch. So the first graph, and both of these graphs are reactions, and it's the potential energy of that reaction versus the reaction progress. And so say a reaction starts off and the potential energy of the reactants is about here. So those are the reactants. Now, to get any reaction started, you have to supply a certain amount of energy, and that energy is called the activation energy, which is symbolized with an E subscript A, the energy of activation. And then once this activation energy has been supplied, you reach this point in the reaction where you have what's called a transition state. And the transition state is almost like a hybrid between, and I don't want you to get it confused with hybrid orbitals because it's different. It's kind of like a morph between the reactants and the products. You don't really have reactants anymore, but you don't quite have products yet. You have this kind of in-between state. So that's the transition state. It exists up here. It is a very high energy state, very unstable, so it doesn't last for very long at all until the reaction continues and you produce your products. And say our products, the energy of the products is down here. Well, I didn't mean to put a P. Sorry. So there's your products. Now, a couple of things that you can get from this graph right here. First of all, this is the energy level of the reactants. So energy of the reactants, that's right here. Energy of the products, that's right down here. Delta H, that's the change in energy of the reaction. Well, if this is our reactants and this is the energy level of our products, then the difference between these two energies is going to be delta H. And in this case, the reactant energy is higher than the product energy, so this energy is going to be released. And when you have energy released, you have an exothermic reaction. Let's see, what else do we need to know? So that's it for that one. So there's that. Then you also have the opposite of exothermic, endothermic. Same exact graph with potential energy on the y-axis and reaction progress on the, I apologize for my handwriting. My computer's getting a little bogged down. Reaction progress on the x-axis. So let's say that our reactants start out right here. And we apply the activation energy. Wow, that's really insufferable. We hit the transition state, and then when we fall back down to products, we actually don't fall that far. And so our product energy is right here. Now in this case, the difference between the energy of the products and the energy of the reactants, this difference had to be absorbed. And so the energy had to come in, which makes this an endothermic reaction. It's so slow. I'm really sorry, guys. So this is an endothermic reaction. Now, the other thing that we need to talk about, and actually I think I'm going to talk about it on a future slide with catalyst, but if we were to add a catalyst to this, remember that a catalyst works to make the rate of a reaction faster by providing a different mechanism that actually lowers this activation energy. So instead of the reaction having to achieve an activation energy or transition state this high, maybe it only has to go that high. And same thing here, it's just going to lower this activation energy, make the reaction easier to move forward, which then makes it go faster. And I'm pretty sure, yeah, that's as far as I needed to get in this one. So there we have part 1.5.